Welcome to Chemvue. Introduction to Chemvue. My name is Barbara, and I'm here with my colleague Roger, who developed this new Pasco application, the newest in our family of software. So it was co-developed by college professors. We got some input along the way. What are the most common data displays and analysis tools that you're looking for? And you will see that this application is not just useful for advanced and college applications. You will also see that, hey, I might be able to use this with a high school or middle school or even in elementary school students. So let's look at the topics that we're covering. Over. There we go. First, I'm going to start with a heat of solution demonstration. And when I go through that demonstration, I'm going to do some very basic data analysis, like just the top level, most common types of analysis tools that you would use. We're going to look at one of the modules that's in Chemvue currently. It's the general data collection module. And then most of the time, you're going to be spending your time in there unless you have some very specific equipment, which would require a different module. And I'll show those in this session. The next demonstration I will do is Boyle's Law, a pressure volume relationship lab to show how manual sampling works in the, I might say, GDC, General Data Collection module. And so again, that's going to be the most common data displays and data collection procedures. Then I'm going to show an acid-base titration. And I chose that one specifically to show the nature of how when you connect certain sensors in the general data module, you will see that the display is smart. So for example, I connect a pH sensor and a drop counter. The software knows you want to do titration, so it will generate a display that will help you get to the data collection even faster than before. If you're familiar with SparkView or Capstone, you're familiar with how quickly you can get to data collection. But I believe that Chemvue will get you there even quicker because of the smart display features. Next, after the titration, we're going to do a different module. So we'll leave the general data collection module and go into one of the specific modules that is developed right around the spectrometer. And it will work with either the wireless spectrometer, which is the one that we're going to be working with, but it will also work with the UV-Vis spectrometer if you wanted to do more advanced or outside of colored solutions analysis. And finally, I'll wind up with the melting point determination demonstration using the melting point module. So currently, there are these three modules in this version of Chemvue that's currently available. But in the future, there'll be more modules available. And as we go through each of these demonstrations, I'm going to be covering frequently asked questions and how to share and save data, how to export, what computer platforms does this work with, and so on. Those are the types of questions that I know are frequently asked, but if I don't cover your question, please do ask your question in chat or Q&A, and we'll answer it for you if you're attending live. Okay, so like I said before, we collaborated with college chemistry professors when developing the software. The software works with Windows or Mac, also iPads, iOS, Android tablets, and also the data loggers that Pasco has available, either the LXI2 or the LX Air data logger. And how do you get Chemvue? Well, you go to pasco.com/Chemvue, and there are a couple of purchase options available. This does have a license requirement, so you can either buy a single user license for your individual or personal device, or you can get a site license for all of the devices on your campus. And go to pasco.com/Chemvue to look at those options or talk to your local representative. Sensors for Chemvue. Okay, so you might have these older generation passport sensors. They're blue and they need an interface to connect to software. Chemvue does support the blue sensors. So anything passport, that's a chemistry sensor, and I'll show a picture of the supported sensors. Those can connect either by the USB connection or whatever your interface does. If you have one of the AirLink for passport sensors, you can also connect either traditional Bluetooth, or if you have a next generation AirLink, that white interface, you can also connect wirelessly that way. So we support current generation wireless sensors as well as passport. I'm going to set that aside.
Barbara, there was a good question that just said, are we going to continue to support SparkView with Chemvue here? And you can address that, or if you'd like, I can as well.
Okay, yes. So go ahead, Roger, and address that question.
Sure. So SparkView will continue to be our general software and available. There's a lot of free options for that. And so that will not go away, and that will be around for quite some time. Eventually, we'd like to see some of the improvements that we're making in these newer softwares be propagated into, sort of a new updated version of that. So it will not be something that goes away.
Yeah, and I will also highlight the types of deeper analysis and error analysis that will be available in Chemvue, which is why you're wondering, well, why would I want the licensed product if I have SparkView? I'll show you, and you can see the extra things you can do with the Chemvue product. Okay, so I'm going to show you another slide. This is a good sample of the types of sensors and apparatus that you can use for chemistry applications at any level. And you'll see that some sensors, like the carbon dioxide sensor, are for gas, and some are for solutions like pH. There's also melting point and so on. This is just a few of the tools, and there's a Geiger counter right there. But you can also, we also have specifically sensors for light analysis. On this image here, you see the light sensor plus the colorimeter. And if you're analyzing light going through solutions, you can either choose the colorimeter. If you are looking at the 6 specific wavelengths that the colorimeter will allow you to work with, or if you're looking for more wavelength options for colored solutions, you could choose the wireless spectrometer. Or if you're looking for analysis of colorless solutions, you can, you probably are interested in using the UV vis spectrometer. And the spectrometers also come with light analysis tools with the fiber optic cables that you can use to analyze, for example, a gas hydrogen tube, to see what the specific line emission spectra are for whatever gas sample that you have. The spectrometers come with with sample cuvette appropriate for whatever instrument that you purchased. You could also get the accessory quart cuvettes for the UV vis spectrometer for those shorter wavelength samples. And also here's the polarimeter, where you can look for the interaction between particles and light rotation if you have a substance that's able to do that. Moving on. Now we're going to do the first demonstration, enthalpy of change. So I'm going to switch my camera so you can get a little bit better view of my setup here. All right. So now this lab is fully written up in the Pasco's experiment library. And what your students will be investigating here in this lab is, how does the solution temperature change when either there is a substance dissolving in solution or there's a chemical reaction in solution. So this demonstration will show a substance dissolving. I've already got about 25 milliliters of water inside my calorimeter. I've got a little flap cut open on my cardboard cover for my 2 foam cup calorimeter here, so that I don't have to take the lid off and maybe add error by, the water is going to be evaporating off the end of the probe. So by making the flap, I can make it easy to deliver the solid into solution and minimize error. So error is the theme here minimizing error is the theme with the setup here. I'm going to get about 1 gram of sodium hydroxide. So this is sodium hydroxide, loves to absorb water from the atmosphere. So I better work fast to avoid error. I'm going to zero my balance and get my 1 gram of sodium hydroxide. And I'm noting that the flakes of sodium hydroxide are different sizes. And I just spilled a little bit on the pan there. So this is about 1 gram. It's 0.98 grams. So I write that down in my data, the exact mass that I got. And now I'm going to switch to Chemvue. And here is Chemvue. There it is. First thing I need to do is connect my sensor. So I turn on the temperature sensor so that I see that the Bluetooth light is flashing on the instrument, on the sensor. I've opened Chemvue. This is what you see on the opening screen right here. If I want to connect the sensor, I just choose the Bluetooth button. And there's my temperature sensor. I tap to connect. And there's a 6-digit code that goes along with the sensor in case you have a classroom full of these. You can see which one is yours. And that quickly, I have the temperature of the solution here. So I'm in monitor mode now. I've got this large digits display with the units degrees Celsius. I've got defaults. This measurement is defaulting to the tenths place. But hey, you know what? I think I want to go to the hundredths place because I think that would help me determine if my solution temperature is pretty stable or not. And it should because it's been sitting here. So if I want to change the number of decimal places, I can just select the measurement temperature here and then go to Edit Data Properties right here. It's at the very top. And a number format, I can change the number of decimal places from 1 to 2. And you can see that right away now I have more places here. And I can see, yeah, it looks pretty stable. And now I understand why it was going from 21.6 to 21.7 because it was rounding. Okay. Now I think I'm ready to start my run. So I'm going to think of a good way to run this. If I want to do more than one run, I'm going to tell myself, well, you know what? I need to make sure that I start when I drop this solid into the solution, I do that at the same time for each run. So for what I mean by that is I'm going to hit start and I'm going to wait till I hit the 12-second mark before I dump in the solid so that when I reach 12 seconds, I'm not rushing. I'm not going to accidentally spill something. I'm monitoring the time on the bottom left corner and there's 12 seconds. So I drop my entire sample in there and I'm going to swirl to keep the solution temperature even. I've got the temperature probe suspended and so that it's touching only the solution. You might notice there's a rubber band here at the where the sensors meet in the cardboard. There's a rubber band on actually both sides of the cardboard, and I can show you that after I'm done with this run. And watch I said Spark-Vue. Watch Chemvue automatically adjust for the data. Look at the y-axis expanding as the data expands, and the x-axis time in seconds is also expanding as the data expands. So we've got auto scale going on. You do have the ability to manually scale the data while data collection is going. I could do that. Or I can wait until the run is over because my hands are occupied stirring the system here. So in the lab, the directions say wait for the temperature to reach its maximum. So you're looking for it to peak, and once it peaks, you're going to continue the stirring or this making the solution for an extra 30 seconds after because that's important for the error analysis in this particular investigation. So some of the tools I'm going to focus on when we do the analysis are the error analysis tools when we look at this run here. And I can see that the rate of dissolving is slowing down. I can visually see that the slope is getting flatter and flatter. And I can use the background of the graph, the gray lines on the graph, to help me decide whether that trend is still increasing or if it's flat, or if it's begun to decrease. I can see it's still going up, but it's definitely slowing down. So I know that I'm close to the peak temperature. And I might have reached it. It might be there. We have some tools that can help us figure out what was the maximum, the max temp. And I'm guessing it's still going up. So I'm going to keep letting it go. I got my eye on the x-axis. And it looks like it's flattening out, so we might have reached the peak. And once I'm sure that there's a decrease in temperature, I'm just going to add 60 seconds more to the run time. So there are some things that are affecting this, how quickly this substance is dissolving and how quickly the energy is getting out. One of them is surface area. Now, you might have noticed that my sodium hydroxide was chunky, and the chunks were different sizes. So if I've got a few large chunks and then some powder, a mixture of those two things, I might have an error because I didn't have, comparable particle size. So that might be something I might decide, do I need to fix that? And do I need to redo this run? I could use tools to decide that. It's definitely flat, but I need to wait for it to decrease. And I also created an error because I was looking at the graph and I accidentally slid the cardboard off of my cup. So I may have lost some heat due to me opening my system when I had not planned to do that. And I can see that there's a definite decrease. So I would say, gosh, at least at 200 seconds, it looks like it began to decrease around 200 seconds. So I'm going to go to 260 seconds because that's important for the analysis. And even I might even go farther than 260 because I want to be sure that I have captured the last, it's actually the last 30 seconds. I misspoke there. So it was 200 as what I guess my peak was. I'm well past 30 seconds beyond 200, so 230 would be right around here. So I'm good. I can stop collecting data, and I would repeat this each time I do a run. Now, I am going to only do one run, but I do have some saved data that I can share for more discussion of analysis. Let me move my equipment aside here. Okay, and something else about error that I want to point out is I do have some of the substance got stuck, some of the sodium hydroxide is stuck to my weighing dish, so that's something I consider when I'm thinking about error. Okay, and now I'm going to go into Chemvue, and let's look at some of the tools in Chemvue. If you're a SparkView user or a Capstone user, you'll recognize many of these icons. Just like other software, if you know one product in the family, you kind of know them all. So your learning curve is going to be shallow here if you've got experience with Chemvue or, SparkView or Capstone. But if you're a brand new user, you'll see that the tools here are pretty straightforward. They're surfaced right at the top level. You can see them all. And the tools that are most commonly used are right there in front of you. So first thing I want to know is, what was the highest temperature so that I know where was my peak? I'm going to get there. I'm going to go through each of these tools one at a time. So this first button, scale the fit. Well, Chemvue did that automatically for me. If I hit the scale button, it just makes sure that the data that's visible is taking up the entire display. This selection tool, data range selection, I might need to analyze only a portion of data versus the entire run of data, and that will become apparent why in just a moment. The coordinate tool. Now, if I use this tool, I can either just touch a point to invoke that coordinate tool, or I can turn it on from the menu here on the right, and it'll put a coordinate tool right in the middle of the graph. If I choose this version of the coordinate tool, I can remove it if I don't need it. Or if I want to know this point over here on the right side, I can touch that point directly and then turn on the tool. Either way, you can move it to where you need to. So, I could search for the maximum temperature this way. I can just drag the gray box and keep my eye on the XY coordinates, looking at the Y temperature and looking for the highest number that way. Or I can use I'm going to skip the slope point tool. I can use the statistics tool here. Let me open that and look for the maximum. You'll notice that there's other options here. I can also choose the minimum or the lowest. I can choose the mean. I can choose the standard deviation, count, or area. This tabular format, I'll show you what that means in a moment. So let's turn on the maximum, and I visually see where is the max. So it puts that the value of 28.53. Let me scoot down so you can see it better. 28.537 is my maximum temperature, degrees Celsius. So that's showing across the entire graph where is that. So no matter where I'm looking on the graph, and no matter looking on the data, I can see, oh, it's way up there. Now, if I don't like how that's displayed and I just want to see on the graph, I can switch from this view to tabular format, and it just puts it into the center of the data. It's not putting it on the actual maximum, it's putting it in the center of the data. Because if you have more than one tool on, let's turn on some more tools, those values might appear in different places on the graph, so it just behaves the same every time. It just goes to the center if you're looking with this view, or you can switch back and turn on the tool that you're interested in and switch it back to the visual format. So you have the ability to toggle between visual and tabular format. So my max is 28.537 degrees Celsius. All right, the reason why I need to know that is because when I estimate the error of how much heat was lost from the calorimeter, because that was not a perfect system, I assume that it actually got hotter than that. So one way to analyze that is you can calculate the calorimeter constant, which requires additional procedure, or you can use the analysis tools here by finding that value, 28.537, which would round to 28.54, using the coordinate tool. So I'm going to drag that 28 till I find 28.54. Probably getting closer there. And since I'm getting close, now I'm going to individually point, and there is one of its value. I'm going to keep going to see if I see it again. Nope, that was it. That was the maximum right there. Go back. There it is right here at 180.5 seconds. So what I'm going to do now is I'm going to turn on the selection tool, and I'm going to, in my head, I'm going to say I'm going to add 30 seconds to that 180 seconds. So it's going to be 210 seconds. So I'm going to grab about 30 seconds of data. So I'm going to go to about 210, which is roughly right here. And I'm going to turn on the slope tool. So I'm going to turn on the curve fit tool right here, and I'm going to apply a linear fit. And what that does is it shows me, if I go back in time to 12 seconds, which is when I dumped in the solid, let me use manual scaling here. I'm going to grab and move the x-axis so I can see the range that I care about. I want to know where is 12 seconds, because that's when the solid first hit the water. There's 12 seconds, and now I can move the graph left or right or up or down so I can put 12 on the origin. That's 12 seconds in. That's when the solid hit the solution. And I want to know, what is the temperature? Where would it have been if I didn't have as much error? So now that I have my 12 seconds, I'm going to bring down the graph and scale out so I can see a little bit more, bigger range, more places on the y-axis. And now I've got a better estimate of where does that linear fit intersect. Right there around 28.4. I can estimate that second, or the second place at 28.43. That's going to be, that's actually a little bit lower. Oh, you know what I think I'm doing is I have the max tool on there. There, now I can see it better. So there's my linear fit. So the maximum is telling me it really should be closer to this value here than what I saw in the data. So that's one way to estimate the true high temperature. I just hit the scale button while I had a selection on, so I'm going to turn that off and rescale. Let me show you why that happened. So I had on the linear fit tool, I had it on a data selection. I had it on like this much data. And when I have that tool on, it only applies to whatever is selected. So my linear fit is right now only selecting this portion of data. If I turn off the fit, that fit applies to the entire run, and as we can see, that that linear fit is not appropriate for this entire data set. It does not overlap at all. So anyways, so I would do a couple more runs, and I would want to know, well, what is the average maximum temperature? What is the average estimated for error temperature based on the linear fit and the looking back at when the solid was dumped into this solution? Now I have some other analysis tools I want to show you before I get to the little bit more detailed analysis tools. So I showed you some stats. If I use the slope point tool, it gives me the change at any individual point. And you can see the black line shows you how much change there is. So there's not much change going on here where the slope, where it's already slowed down. But if I go to where it was changing quickly, you can see that the black line is a lot longer, showing you there's greater change here. The rate is the distance of the line, or the length of the line, is proportional to how much change is happening between that point and the previous point and the next point. So it gives you an idea of how much is changing point by point. Then you saw that there were more than one kind of fit that you could use. We're going to use a different fit for the Boyle's Law investigation in a minute, but we used a linear fit. Like maybe you're going to use Gaussian if you're going to do a polarimetry lab. Then there's this tool here, the add note to point, the annotation tool. So if I turn that tool on, I can enter a note here, added solid. So I can point out exactly in the data set where did I add the solid. So there, I can drag it to where I want, and I can move that bubble anywhere I want. And I added it right around 12 seconds. So now I can rescale to show the entire data set. And I have some note of something interesting or worthy of noting on my data. Add y-axis. I can connect additional sensors using the Bluetooth icon here, and I can add another y-axis. Maybe I want a second temperature sensor so I can compare and see, you know what? I need a sensor that's going to get the temperature faster because I don't like what temperature it gave me. It gave me actually a lower temperature at the maximum when I use the error estimate. So maybe I need a quicker sensor, and I could maybe use a fast response sensor. and I can compare the two at the same time, I would just select that temperature, different temperature sensor here on this y-axis, and I added it using this tool, add y-axis. If I do have more than one sensor and they are of the same type of measurement, I would probably, it is likely that you'll want to make sure that the ranges are set to the same on either y-axis. So right now on the right, the range is -10 to 9. If I turn on the Keep Y-axis Align tool, now the y-axis ranges are identical on either side. So that's a useful option as well. Now, some other things in Chemvue that you've not seen yet in our other software products. The ability to set preferences that will be saved from every time you open Chemvue and close it and then reopen it. If you go to the main menu to Preferences, you can turn on dark mode. So there's dark mode. So notice how the contrast, if that helps you, you're working at night, or it just helps you see it better, you can enable or disable dark mode, and it will remember your preference the next time you open. When you're using the Geiger counter, it'll beep when it gets a reading. So that might be annoying, depending on what you're doing, what type of investigation you're doing, so you can turn it off by default. You can also select your language here. And showing connecting lines, by default, the lines are connected on the graph, and you can't really see that because we have a high sample rate here. Let me expand the graph so you can kind of see there's lines between each of the data points. If I can turn that off here in the Preferences menu. So I turn it off, and that might make it easier to see if you have a linear fit and you're trying to decide what's the most best fit, and it's more than just a straight measurement. Maybe you transform your data and you want to see what's the best fit for maybe the inverse or the natural log, then you might want to turn off your data points, your connected points. So I'm going to turn that back on. And showing only the current run recording. That's on right now, and here's what that means. If I start a second run, I see my current data right now. The green line is what's recording now. It looks like run 1 went away, but actually if I go to the legend and I hit the check mark, it makes that run reappear. And I can scale the graph to include both data at their biggest display. Some other options I have, so those options I just showed now, those when they're in the Preferences menu, that will, your software will remember your preferences, and that will occur every time you open Chemvue, but you can always turn them off if you prefer the other options. Now, some of everything else that you apply will only apply to the experiment that you're currently working on. For example, that linear fit, this note. What if I don't like a run 2? What if I don't like green? I can change the color of the run. What if I don't like my sample rate? It's too fast. There's too many data points. I can change that too. Let's look at the bottom left over here. So here's the experiment clock. It might have been harder to see at the beginning. Sampling options. This is the menu where I can change the sample rate, how fast or slow the data is collected. I can slow it down by maybe every 2 seconds. That's 2 seconds, every 2 seconds, every 5 seconds. Or I could speed it up and say 5 hertz, which is 5 samples per second. Let me put it back to 2, which is the default. And we set the defaults based on what we believe are the most common requested sample rates based on the sensor. I really didn't need that last run, so I can actually hit the trash button and delete it if I want to. I can also delete it if I go into the Manage Runs menu. I open that menu, and I can delete run 2, or if I want to keep it, I can rename it next run, because it really is not of anything important here. And I can change the color of the run as well. I didn't like green. Well, I like green. How about a darker green? And I can set it to that color. And now I have a new name on that run. I have a new color on that run. And even though both these measurements are temperature, they are independent runs, so they are allowed to have independent colors. Finally, the Graph Properties tool. There are some additional error analysis that you can do that right now you won't see in SparkView. You see that in Chemvue. So I'm going to open. There are ways that you can share data in Chemvue, and one of them is to save your file, just like any other file in any other program. Save it to your device. I have, by using Save or Save As, you can export the data, and what that will do is it will create a CSV file, which you can open in another program like Excel or Google Sheets. and do analysis with those programs. Or you can also do the snapshots icon, the export page image button. And if I do that, it'll take a screenshot of the entire data display. So, and you can rename it to whatever you want, and it saves it as a PNG file. You could also just do a traditional screenshot based on whatever your method works for your device. Okay, so let's look at I'm going to open a file I saved earlier. I did 3 runs of the sodium hydroxide dissolving in water. Here they are. So I have a question. Are my 3 runs, did I make a big enough error to have to redo any of these runs, or can I just chalk up this variation to unavoidable experiment error, or is this because something else unavoidable, like the temperature sensor I had? How close is it to its error range, or its accuracy rather? So I have all 3 runs visible. Right. Again, this is just the same experiment I just showed. 3 runs. Now I'm going to show how error bars can help you decide whether there's a significant difference between these 3 runs. And you're looking at it thinking those look the same. But let's just use the analysis tools just to see. So I want to turn on error bars for temperature. If I want to know what is the accuracy of my sensor, I can click this link here that says View Sensor Information. So this is new. And it takes me right to the web Pasco's web page for this product, this specific temperature sensor, and it tells me the accuracy. My accuracy is plus or minus 0.5 degrees Celsius. Knowing that, now I can go back into Chemvue. I can turn on error bars for the fixed range because I know it's above and below plus or minus 0.5 degrees Celsius. Error value above 0.5. So now it's putting half a degree of error above the actual data. And then below the actual data, 0.5 above and below. And when I look at my error bars, I see that all 3 are overlapping on all 3 runs, and they're not significantly different, so I can proceed with my analysis here. If these bars do have a larger a gap between them, then we could do further analysis, or we could just say these are different enough and I have to redo something. So I have better reproducibility of my data. So we're looking at how these 3 runs are pretty much within the margin of error of the sensor, so they're all okay. Okay, so that's one use of the error analysis. Another thing you can do with error bars, let's change from fixed range. Let's do a cross-run average. So Chemvue can take all the runs that you want. Right now, run 1, 2, and 3 are all selected, and you can choose or exclude any number of runs that you want. I'm going to turn off error bars because I really just want to see the average plotted, and I say okay, and look, it added another run called cross-run average. Let me scale the data so we can see all 4 now. So run 1, run 2, and run 3, I'm turning them off because they are real data from primary data from directly from a sensor. Where cross-run average here, this is the average of the 3 runs. So now if I wanted to, I could get the average maximum temperature. I could do the average error analysis and run with that for my analysis on this lab. So the cross-run average is also a new thing that you don't see in SparkView or Capstone. Okay, so there's also the ability to add a calculation, which I may or may not have time to get to. If I have time, I'll get to it. I'll show it. If I don't, there is plenty of help available from Pasco website. Let's go to the presentation very quickly. So I went over how to save and share files. There's the option to save just as a file to your device. And anyone with Chemvue can open that file and see the data, including whatever analysis you left on there. That file will open with the exact analysis still on there. You could export as a CSV file to be opened in a different program that supports CSV, or you can use the screenshot option that's built into Chemvue, or you can use the screenshot feature for your own device. The experiment that you just saw is available in the experiment library for free. It's at pasco.com/freelabs. If you go there, you will see this lab. It's called, I believe it's called Enthalpy of Solution or something similar to that. But if you want to see all the Chemvue labs that are available, go to the experiment library. This is what it looks like when you go there. There's a box here that says search phrase. Type Chemvue in there. And when you type in Chemvue and then you click the filter button, all the Chemvue labs, all the labs that are written specifically for the Chemvue software will come up. And we're adding new labs to that all the time. So check it frequently. There's all kinds of labs that you would do in your general chemistry, freshman chemistry in college, or even some of the AP labs, or even general regular, ordinary chemistry in high school there. Also, there's help built into the software. If you go, let me go back to Chemvue so you can see how to get there. If you go to the main menu and you go to help, it takes you to the help website. And you can just type whatever search term in the search bar there. And if you want to know how to calibrate a pH sensor, you start typing it and it narrows it down and you can find the article you're interested in and click on it and get help right away. Another way to get help, let me close that. Another way to get help is by looking at our videos. We have a video available that has a overview that kind of goes over what I went over and more in 16 minutes. It's a rapid fire, very thorough, but yet there's more kind of features in this video at this link, which Roger will drop in chat. And also, if you go to pasco.com/videos and open up the video library, just search in there. You can search Chemvue or you can search for any video topic that you're interested in learning more about, whether it's Chemvue or a sensor or a lab that you might have seen. Okay, let me go back to, actually I want to go back to presentation here and wrong thing. There, okay. Now, I want to go on, let's do some manual sampling. So here's how that works. I'm going to switch my camera real quick. There. Okay. I don't need this balance anymore, so I'm going to move it out of the way. And then let's get the Boyle's Law set up here. All it is a pressure sensor, which comes with a syringe. So we're going to look at the pressure volume relationship. And I don't want a whole bunch of data points collected at the same time automatically. I want to control when I collect data because I want to wait for the volume to get to wherever I set it on the syringe to get the pressure of that volume of air that's currently trapped in there. I have it at 30 milliliters right now. So I'm going to start a new experiment in Chemvue. The top left main menu, I'm going to choose New General Data Collection Experiment. I don't need to save my work. And here I am in that screen before. I still have the temperature sensor connected. So I'm going to go to the Bluetooth menu. I don't need the temperature sensor, so I can disconnect it. Now I'm going to turn on the pressure sensor and connect it. Tap to connect. Just like that, we have the pressure connected. Some other displays I haven't shown you yet. There's a table display. So it automatically takes your measurement and puts it with time for pressure sensor. Doesn't do that with all sensors, but it does for this one. Here's a graph. It automatically assigns pressure to the graph on the y-axis with time on the x. And on this third display here, the graph and table page, it automatically puts time, x-axis, here on the graph, and pressure, y-axis here, the thing I connected, automatically smart puts it on the y-axis. But I said I wanted to compare pressure and volume. So I have this new table display now. I've got some new tools for the table display. I can add column. I can put a new calculation column. That means I can, if I want to do some transformation, like I want to do the inverse volume or something, I could do that. User entered data. That's what we're going to need because there's no such thing as a volume sensor. Volume is something that we measure physically with an instrument like this. So I'm going to change time. And the reason why I'm going to pick this column is because Chemvue will take the first column on this display and put it on the x-axis. So keep your eye here on time on the x-axis on the graph when I change it here. So I'm going to pick time. I'm going to tell it I need a new user entered data. I'm going to name the measurement volume. And the units are going to be milliliters. I don't need any decimal places here because my tool isn't graduated enough to give me any decimal places. So I could put 1 if I wanted to, but I'm good with whole numbers. So I'm going to say OK. And now look at my x-axis is automatically changed to volume because that's the first column in the graph, while pressure remained the same on the y-axis. So the values I'm going to use are 60 milliliters, 55, 50, 45, 40. So changing it by 5 every time. So I can see what is the pressure volume relationship. 15, and 15 is probably the lowest I can go. And the sampling options now, we're going to do a little more with that. So periodic means it's going to collect data at a particular rate. So I'm going to change that to manual so it only collects data, records data when I say to record. And now I can say, OK. So I'm ready to start. I'm going to hit start. And I need to set the volume to 60 milliliters. on my syringe. So I'm going to turn it. It's going to be a little difficult. Not impossible, but difficult to do with no lab partner. So I wait for that to stabilize, and I'm going to hit the keep check mark when I know that it's stable and temperature equilibrated. Give it a second to do that. And now I'm at 55. And look at my pressure. It went up a little, and now I'm going to go to 50. And notice that when I keep a number, it turns black. When it's not recorded, it's the color of the run. It's green. So now I'm going to go to 45. So that's one way for me to tell whether I've actually kept that value or not. Pressure seems to be going up as volume is going down. That's what I see initially, my initial impression. And I also see that on the graph as well. I'm going to go to 35 milliliters, down to 30, 25, 20, and 15. This one's a struggle. I can do it. There it is. Okay, I'm going to hit. I have no value to do anymore. There's no more volume. And I have my final volume has the black digit, so I know that it recorded that value, and I hit stop. If I did make a mistake, as long as I'm still recording data, I could always go back to a previous measurement and redo it if I need to. So that's nice. But I've got everything, and I'm satisfied with my graph. It looks pretty like there's definite trend here. So I can hit stop. Now, again, the graph auto-scaled for me. And by the way, in case you're curious, yes, you can change units if you don't want kilopascals for pressure. You can change it to atmospheres, and it changes both the table and graph values for you so they're consistent. Okay, anyway, we can do an analysis of the data here. We can see that there's a trend, so we're going to want to apply a curve fit. Let's see, does the linear fit the data? No, it doesn't not. So, oops, wrong tool. To get rid of I can just click the bubble and hit the X. Now I can choose a different curve fit, and eventually you would find that the inverse fit fits the best. And you can use the parameters in the bubble that comes up, the y equals ax plus b, that's my relationship between the x and the y measurement. The b value will drop out of the equation because the b is the y-intercept, and pressure, if you intercepted pressure at 0, that just doesn't exist. So you can drop that out of the equation. And you can get the value of A is the constant that represents the relationship between pressure and volume. So you're essentially looking at Boyle's law here. You're able to make predictions about pressures and volumes that you didn't measure because the prediction based on that equation from the fit will tell you and make predictions as far out as you can make it go. And then you can check and see if you were correct in your prediction by looking at the linear fit and plugging in values for X or Y based on that constant of 29.3 in this equation for inverse fit. So it's basically you can discover Boyle's law. Your students can do that. Okay. So, Roger, are there any questions we should go over?
No, we're looking good.
Okay, great. Okay. So that is manual sampling. Next, we're going to run a titration. So I'm going to start a new general data collection, and we're going to go to the modules in just a moment. I don't need to save my work here. Let's do a titration, and I'm going to switch my camera again because it's easier to see this setup like this. Okay. My sensors aside that I don't need anymore, and I'm going to disconnect the pressure sensor. And now I want to connect my pH sensor and my drop counter. So I've got a pH sensor. I've previously calibrated the drop counter to work with my titrant sodium hydroxide. I've got a strong base here, and I've got an unknown acid. And notice how I've connected two sensors here. It's giving me the value for pH with no units, and the fluid volume, well, it has 1.78. I think I might have turned it on when I was moving it over. I might have given it a little bit of data that I didn't intend to, but that's okay because anything on this screen, this monitoring screen, is not recorded. When you're on the other screens, however, once you hit record, then those values are recorded. So you see it's not going to keep my values there. Now, I told you earlier that the Chemvue is smart, where it knows that if you're connecting a drop counter and a pH sensor, it knows that you want to do a titration. So instead of putting time on the x-axis, it puts fluid volume and on the x-axis and then pH. So you could still do a titration manually. You could still put a burette here. How would you do it? Basically, the way I just showed you with manual sampling and Boyle's law, and you would put volume on the first column, and you would be manually entering the volumes from your burette. So it's pretty much the same setup, except you're using a pH sensor in that case. So now that I've got my drop counter and my pH sensor connected, I got these solutions prepared ahead of time, so I had to cover them so they wouldn't evaporate and over time. And I've got in my beaker, I've got an unknown acid. I know it's hydrochloric acid, but I don't know its concentration. So I can do a titration to figure that out. And I'm going to move my syringe, which is filled with the titrant. I've already adjusted the stopcock so that the drops come out one at a time, which the drop counter needs to see drops come one at a time, or it won't be able to count the drops. And now I've got my magnetic stir set up here, and I have to put my pH sensor into the drop counter right here, move the storage container, and rinse the probe before I do that. And I'm not that concerned. I'm not concerned about adding additional distilled water in there since it's already dilute anyway. I want to make sure that when I put that sensor into the beaker, I adjust things so that the bottom of the sensor is not touching the bottom of the beaker. So it's actually touching the bottom of the beaker. So I got to raise things up a bit, a little higher. That's probably okay. Well, here's how to adjust for the titration. Now I'm visually looking and making sure that my sensor is not going to touch the bottom of the beaker. It's touching solution only and won't touch the magnet when I turn it on the stir plate. Additionally, I'm making sure that the black line that you can see there's a little rubber part of the sensor that black line is totally covered with distilled water. So I'm going to add a little bit more water. So I'm going to add that line so that when I turn on the system, everything is covered in solution. Okay, so I'm making some adjustments so that the magnet does not hit the sensor when I turn it on. Now, let me turn on my stir plate. And I want to get the speed fast enough to get a little vortex in my beaker going. I'm adjusting the height of my drop counter so that the drop goes through the drop counter window and into the beaker. And I also want to change the position of the beaker so that the vortex that forms near the magnet goes straight into that, or so the drop comes from the syringe directly into the vortex formed from the stirrer. I don't want any splashing going on, so that looks like a decent speed, maybe a little faster. Okay, and I'm going to hit start on Chemvue. I'm going to start recording. And nothing happens. I've got a purple dot there and there's nothing happening because there's no drops going through the drop counter yet. So I've got to open up the stopcock. And now the drops are coming out. And it might be hard for you to see with the view you got there, but we've got drops coming out one at a time. And as soon as those drops started coming out, now you've got data being plotted, pH and volume data at the same time. And you're probably guessing this is, I told you it was hydrochloric acid, so it starts pretty low. And it's going, starting to increase. I can move the legend out of the way while the data collection's going. Starting to increase faster now. By the way, I put in 10 milliliters of acid into this. Oh yeah, we're approaching equivalent. We're approaching equivalent. And it's already well past equivalence, and I'm leveling out again. So I already have that fast. I have enough data to do analysis here. I'm going to stop recording data. Turn off my system here. And move that aside. All right, some analysis. This lab also is available in the experiment library. So for analysis, you could do a selection of the most vertical part of the data, where it's the straightest, put a linear fit through it. See, that's pretty straight, and look to see where does it cross the line there, well, that's about at 7, pH of 7. So that's further evidence that yes, this is a strong acid. I can do all use all the tools I showed earlier for scaling. In fact, I can scale to fit just that one portion of data. And there is right here is where it crosses right around 7.4. And what is my volume at 7.4? It's about 10.13 volume milliliters of base. So now I can do my calculation, M1V1 equals M2V2. And just like that, I can figure out the concentration of the acid. And that full write-up, all the procedure and how to do the calculations is in the lab. You can find that in the experiment library. So that was a quick, nice, fast way to do titration. Here's a quick, fast, nice way to do some spectrometry. I'm going to start a new experiment in Chemvue, but I don't want this time a general data experiment. I want a spectrometry experiment. So now I'm using the spectrometry module. Don't need to save that work. I'm going to connect my spectrometer. And using the Bluetooth icon, oh, hey, for those of you that know the spectrometry app, it's now built into Chemvue. So no more having to use 2 apps. It's all in one. I don't need to have my pH or drop counter connected anymore. But I do want to connect my spectrometer. Okay, so I'm going to grab the USB to connect it. And then turn it on. So I can either connect this wirelessly or by USB. Oh, it doesn't want. Let me see if I can get it to turn on here. Oop. Wrong one. There. A second here. All right. Okay. So connect this guy. There we go. And tap to connect just like the other sensors. And I'm connected. Okay, so first we're going to calibrate with I made all these solutions. Again, this lab is going to be in the experiment library. So everything was made with distilled water. So my blank here is distilled water or deionized water. And I'm going to do my calibration with that. So first I calibrate dark. With the light is on this side of the instrument. The light passes through the sample and goes to the detector here. And I'm going to calibrate with light on. So calibrating light. And it's already done with calibrating. Now I'm ready to collect data. So I've got a series of solutions here at different concentrations. I'm going to start recording. And now I can see the signal for this substance. I can either show absorbance or transmittance just by clicking the Y measurement. Move this out of the way. And my absorbance is just under 1, which is good. So I think I'm going to use this, to pick this for my analysis wavelength. The peak is up here at the orange wavelength, so I'm going to turn on the wavelength selection tool and move my coordinate for wavelength selection to the peak there and select the check mark to get that black line saying, hey, I'm going to do all my analysis at this peak of 620.1 nanometers. Since that's a valid concentration, it's not too high or too low of an absorbance. Now I'm going to do a Beer's law curve. The concentrations that I have are 1 molar, I've got 0.83 molar, I've got 0.67 molar, 0.5, and 0.33 molar. So in a flash, I'm going to get the absorbance values here. This for the first one. The next concentration, I'm going from high to low. You could also go from low to high. I'm going to work quick here because we're running short of time, and I do want to show the melting point module. So next, you can see that we've got a Beer's law curve forming here. Concentration and absorbance are directly comparable, which means that we could set up this calibration curve here and figure out the concentration of an unknown concentration of this blue solution. So I've gotten all my data. It's automatically manual sampling. I can scale it. might be hard for you to see that there's the green right there. This display, this rainbow, if I want it out of the way, I can turn it off with the live scan display option. That's pretty linear data. Here's an option where I might want to turn off the connected data points. So now I see just the data points, and I can put my linear fit through there and see that's a pretty good, darn good fit. So if I have an unknown concentration like this one, I can determine what it is using this linear fit equation, y equals mx plus b. My slope m is 0.811, so I plug that in for m. I can subtract out the b value and plug in b right here. There's my b value. The y is absorbance. How do I get that? Well, let me go to the unknowns table and get the absorbance of this unknown concentration solution. It happens to be 0.518 or 513. And stop recording data. And if I plug in this absorbance value 0.513 for y and I solve for x, I'm just going to pretend I know what that is. I don't have a calculator with me. But let's just say that that is 0.56 moles. And then it plots that point for me right here, and it says, you know what, you're close, but not quite right, because you're green still. Got a green square. Let's say it's 0.52. You're really off there. Okay, how about because I got a red X, how about 0.58? You're getting closer. Got this yellow X, and so on. So if you actually did the math, you would get perfectly on the line. Closer you get, the color and the shape changes. Okay, so for those of you attending live, we are officially out of time, but I am going to continue the recording and continue on to show the melting point apparatus, which will take just a couple of minutes. But if you are unable to continue on, since our time's up, feel free to log off. We will continue recording and send you that recording. So thanks for attending. And those of you that can't stay live, it's just a couple more minutes to get to the melting point module, and then we'll answer questions live. Let me finish this PowerPoint here for those of you attending live. The information for your regional rep, please let them know if you have any questions about any of the equipment you've seen today, or Chemvue, the app. And you can scan that QR code. It'll take you to that page on pasco.com. Now I'm going to switch back and go finish the kinetics portion of the spectrometry investigation. Let me switch back to Chemvue. So, okay. So now that we've got the data for the concentration absorbance values that are known and unknown, what we can do is we can do a kinetics experiment using that first solution, the 1 molar solution, and I can see what is the rate of reaction if I bleach this blue solution to clear. How fast is it going? What is the order? Is it 0, first, or second order based on the analysis tools that are built in here using this option, the concentration over time page. Notice here there's a light bulb. There is ability to do light analysis with a fiber optic cable. We don't have time to show that, but that is an option that I talked about earlier. So I'm going to take a 1 molar sample. Let me switch back to the zoomed in camera. I'm going to add a few drops of bleach. 3 drops. And I might have error there because I took my time kind of getting that bleach in there. I'm going to invert a couple of times to make sure it mixes well, and then I'm going to start recording. And we're going to let that run go for a couple of minutes. So while that run is going, I'm going to set up the melting point apparatus, and that run's just sitting there. Well, so let's use our time wisely and talk about this instrument. So the melting point apparatus, let me switch the camera again. Okay, this instrument, it heats a sample inside of the, where you can't see. Let me see if I can get the camera on there. Maybe you can see a little bit better. There we go. So you can see there's a metal part in there, and I've got 2 glass capillary tubes sticking up. They've both been packed with a sample of not so fresh salicylic acid, because when I opened my sample bottle, I could smell vinegar. So I already knew that my melting point was going to be not what it was expected. It's going to be somewhere above or below the expected point. So the thing I love the most about the melting point apparatus is while it comes with an ordinary eyepiece that you can look at and you can see the crystals melting and you can measure the temperature with the software. What I love about this is you can swap out that eyepiece for an optional camera piece, and it works with the software to coordinate the visual melting with the actual measured temperature. And it keeps those points coordinated throughout the run where it matters the most. And that's what I'm going to show after this kinetics reaction is all done. So the camera is a separate accessory. So the melting point apparatus comes with some capillary tubes and an eyepiece. Yeah, this would be optional camera. Okay, so back to the kinetics. We like to let this run at least 2 minutes. So we're almost there. And I'm going to stop recording data here. And now what's nice is I've got absorbance on the y-axis because it's a spectrometer. But since I did that Beer's law curve where we had the known solutions and we calibrated for the known range, I can change from absorbance to transmittance to concentration. And these are actual concentrations based on that Beer's law curve. So you could say that these are real representations of the true concentration at a given time across the entire reaction. So now let's do some curve fitting. We want to see what the most linear is, right? Because that's how we analyze for reaction order. So if it was a 0 order reaction, this curve would be the most linear. Doesn't look like it is, but let's just see. Let's keep going through. I can use this button up here, this quick calc button, to change to the natural log of the concentration. And if we apply a linear fit here, that's a pretty good fit. And let me change to the next quick calc, the inverse concentration. And this would be a second order reaction if this was the most linear, but that's not the case. It really looks like it's that first order reaction. The natural log has the best fit, which it absolutely does. Absolutely the best fit, but you could also use the R value. The R here is -1, which is a very good fit to evaluate how, if you need a tiebreaker between two fits that look very close. You can use the R value and the root mean square error to evaluate which are the better fit. So we've determined that this is a first order reaction in record time using our spectrometer module. But now let's move on to a different module. I'm going to disconnect that spectrometer and now connect the melting point. Let me close out of Chemvue and open a new Chemvue. Okay. And I'm going to use the Bluetooth icon to connect that melting point apparatus. So I turned it on. It is searching for the signal and I tap to connect. And I have this display now. This looks different, right? I have a camera that I purchased, with my accessory here. So I'm going to plug that in. It's a USB connection. And when I plug in that camera, there it is. It looks a little blurry, so I can adjust the focus by moving the camera manually, focusing it. That's pretty good. What I've got here on my preview on the left here is a sample that I ran with yesterday. I melted it. I already did the analysis on it, so it's already melted. On the right, I have an unmelted sample, so you can see the difference in what they look like. This is already solidified. But as you're setting up this experiment, it starts with a default profile, quick ramp. See this part of the graph here? That's how very quick heating up, where you want to make it stop low enough below your expected melting point to not overheat the sample. If you don't know what the melting point is, I would say, yeah, go ahead and leave it at 250. Go ahead and overshoot it and do a second sample when you know when it's about where the melting point is. You can change it by changing the temperature down here. Yesterday, my sample I set to 128. So I'm going to set up the profile. I'm going to open a pre-saved data file so you can see what it looked like in the end. Because this would take, it gives you the estimated time, right? So what hold does is it keeps the temperature stable at whatever your top of your quick ramp was. So we'll keep it at 128 for 10 minutes, which I recommend leaving it there. You can change it maybe to 5, but I like leaving it at 10. Prompt is that question mark. It says, it'll make a pop-up on your screen saying, hey, are you sure? Do you really want to start heating it up again? Because you might not be looking at your screen, or maybe you don't even have a camera and you're not looking at the, maybe you don't have a camera and you're not looking at through the eyepiece, and it really lets you know, hey, should I start heating it up again so that you don't miss the melting point? But if you got a camera, it's all recorded. So, I'm going to show how that works. Then after a pop-up message comes here, after your hold time has ended, you say, yes, I'm okay. Okay, I'm ready to go on to the next step. So then it starts the image capture. If you have a camera connected, it'll start taking pictures with the camera every 10 seconds, or you can put it as low as 5, or you can make it take space out those captures even longer. That ramp. So the ramp is how long it takes to get from the end of the quick ramp temperature to the highest temperature that you want it to go. So for me, that was 138, I believe, or somewhere around that, because I knew I had a contaminated sample and I just wanted to get it way above the melting point. And the time that it takes, well, you want a good rule of thumb is no more than 2 degrees per minute. You can make it go slower or faster than that, and you can change that rate by changing the time. So there's a full write-up for this lab. I'm going to hit start. So now it's recording data, and what it's doing is it's doing the quick ramp. I've got this display here that shows everything. If I go to the next tab while it's running, I can do this. Look, it's showing me the graph. So I'm seeing the live graph form of the data. And when you're done with the run, which I'm going to go back to the first tab, it says it's going to be about 40 minutes if you go with this, give or take a few minutes. So after that 40 minutes, you might see data similar to this curve. Will be similar to it. The temperature is being displayed right here. It's not recording yet, though, because we're not going to be recording images until we get past that prompt, until it goes to that second heating. And that's because every time you take a picture, it's making your file bigger, and you don't want like 200,000,000 images to crash your computer. So we make sure that we're just taking pictures at the time where it's really critical, when it's very close to that expected melting temperature. And finally, you can go to that third tab, which just shows a full screen of the image. So I'm going to stop this run. And because I'm going to turn on the cool so I can cool it down fast if I want. I can also calibrate it. I'm going to open a pre-save file so you can see what it looks like if I were to go through with the entire run here. And my run actually took 25 minutes because it had slightly different hold time. So I've opened my previously saved work. I need to switch to playback mode because I'm just watching some data that's already been recorded. So now that I'm in playback mode, I have the ability to advance to play some recorded data from yesterday. I can change the frame rate. I'm going to change the speed to 32 times so you can see over time. Watch this one. You see it's glistening. And then you start to see there's definitely liquid forming at certain points. So to get the beginning of the melting point range, I can pause. I can move back my playback to where I think I first saw definite liquid forming, which is somewhere, got to figure out where is it glistening, where is it liquid. It's probably somewhere around here. And I can go frame by frame by frame by frame. And so it tells me the time here, frame by frame by frame. And I can look on this display also and get the temperature at each frame. See the temperature changing as I'm going frame by frame. So there's no way for me to miss it's very easy for me to not miss the melting point this way because I've got all this recorded evidence, the aligned image with the temperature. So I did go way over time, so I apologize for that. But if you are still live, thanks for watching. And I'm going to switch back to the list. And thanks for watching, and I'm going to end the recording now.